Okay, what are the equilibria points for a nonlinear dynamical system? Let's create a very abstract example. You have a two-dimensional system, like a computer game, where you have a terrain, and on this terrain you place a ball. So, a very simple ball. If you, for example, place it in here, here is your ball, it can move, it can fall down or go up if you push it, and go left, right. So, if it is on a relatively flat terrain, it will stand still. Okay, what if you place your ball on a slope? Of course, there is gravity in our world, I will denote it as G, so it will fall down. How far? If there is friction in this world, it will go, first of all, it will gain velocity down, but it will go up to, for example, here, due to friction, and then fall down, and that's a very neat word, and it will stabilize itself at the very bottom of this valley. Okay, so it basically just rolls like that and stabilizes. That's an equilibrium point. This means that when you place a ball on its own in here, when you have an empty environment and you just place your ball in here at the bottom, it shall not move. So it's in an equilibrium. Now, it can be a stable equilibrium or an unstable equilibrium. A stable one, a locally stable one, is when you push your ball and it returns to this point, only this point. So, if you push it to your left, it should return. Yeah, of course. But if you push it to your right, oh, that's not so simple. If you only push it halfway through this hill, of course it will return. So it is locally stable. We have proven that our system is stable up to here. But if you push it too far, it will actually go to this terrain. So you have an area of stability. You have an equilibrium in here and an area of stability. Okay, but what if, for example, there is a piece of a flat terrain over here, exactly flat? Is it stable? Well, it is an equilibrium. I can place my object in here and it will not move, so it meets the definition of an equilibrium point. But if I mark this point as x1 and then I test for stability, for example, I push it to the left side, it will roll and it will actually stop in the next point. So this is another point. It's not the same. So this point was not stable. It was an equilibrium, but not a stable one. It didn't return to the original point on its own. Okay, so what kinds of a terrain can we have actually? Of course, we can have a valley, where you start on the edge and you go down to the middle. You can have a flat one. Good. Or you can have a hill. So, if you start on the edge of the hill, you will fall down. So, it's not stable. If you start at this edge, you will fall down. It doesn't really matter where you start, except for one special point, the very top of the hill. If you start at the very top, you are in an equilibrium. A highly unstable one, of course, but it doesn't matter how unstable it is right now. It is unstable, but it is an equilibrium. So, what is an example of a real mechanical system like that? Well, a pendulum, of course. Our little pendulum has an equilibrium point at the bottom. So, if you just leave it here in a gravity field with some friction, it will just stabilize itself here. So, well, it is an equilibrium point. You stop moving eventually in here. It is also stable, but we will check that later. But if you just push it upwards and place it here, Well, if you do it perfectly, it will just stand there. So you have at least 2 equilibria points. Okay, why did I say at least? Because those 2 are in a mechanical sense. You can see them. Physics tell you that those are the very simple 2 equilibrium points for the pendulum. What about mathematics? How do we prove that a system, an abstract system, has equilibria? Well, let's take the pendulum. The pendulum model was the x1 is the position. The change of position is velocity. The change of velocity is, and now I need angular acceleration. I will go from memory. This is the basic model for a pendulum with friction coefficient. No inputs, just a very simple pendulum model. Okay, an equilibrium point is a point where nothing moves. So let's freeze, from a mathematical point of view, everything that is able to move in the system. So let's make it, well, constant. So there are a couple of time variables in here. For example, x1 is a variable based in time. When you draw a picture, you always add an information about time. And when you draw another one, you may notice which variables changed over time. The length was the same, the mass was the same, but x1, yeah, it did change. So x1 depends on time. x2, the velocity, also can change between the pictures. So x2 also depends on time. So I need to freeze those velocities, those states, so the position and velocity. So if I freeze them, this means they no longer have a derivative. They are no longer changing over time, so the derivatives are automatically 0. So everything on this side will be 0. And now you get a funny information. If those 2 are 0, this means that x2 is 0 from the first equation. Okay, so this part will be 0. So I am left with, this is 0, this is 0. 0 is minus GL sinus x1. That means that I can divide by those, like this. This is a constant. I will be left with sinus of x1 is 0. When is the sinus function 0? If you were to draw a sinus function, it starts at 0, goes up, down, and ends at 2 pi. This was my x1, yeah, this was x1. And this was the value of sinus x1. When is it 0? 1, 2, 3, 4, 5, 6, 7. There is an infinite number of points where it is 0. And in general, they have a form of 0, plus minus. This is pi. So I just need another number, k times pi, where k is 0, 1, 2, 3, etc. Okay, seems easy enough. That means there is an infinite number. What does it mean in a mechanical sense? Well, my pendulum got complicated. I got here x2 0, x1 as like that, so x0, my set of equilibria points, is x1 0 plus minus k pi, and velocity 0. So my first one is at the bottom and not moving, velocity 0. This is my first equilibrium. Then I have plus k pi, plus 180 degrees. That's my second equilibrium point. And, of course, not moving, velocity 0. Then my third one is 2 pi. So that's my third one. Then I'm going like this, that's my fourth one, and so on. So these are just multiple turns of the pendulum. I am getting an infinite number of them because there is an infinite number of turns I can take with a pendulum. From the physics standpoint, those two are the same. Those two are the same. But from the mathematical point, those are the next half rotations. So my control system will be a little bit strange if I were to, for example, add something in here to control it. Because from this standpoint, from the standpoint of this precise equation in mathematics, I can move from this point to this point. Yeah, it's absurd, but you have to take it into account when you introduce a description of a system. Descriptions that use trigonometric functions are never perfect. Okay, so I've got my equilibrium points. The question is, which of these are actually stable? But I can check this using the Lyapunov method, for example. I will introduce it in a bit.